Hi everyone and welcome to this class. My name is Sriram Shankar Narayanan and this course is titled Principles of Programming Languages. The number is 3155. Okay, this is going to be the introductory lecture for this course. I would normally talk about class logistics in a lecture, but for now I'm simply going to say please read the syllabus and please look at the software installation. You're going to be asked to install Jupyter notebooks. So Jupyter with Scala kernel. And there is a website called coding.csel.io. But this website has some issues with it going down sometimes and not being available, or occasionally students have mentioned that they have lost files on this website. So I'm sure everyone is aware of this website, but use with caution. We have provided some options for installing Jupyter plus Scala natively. Okay, so for the rest of this video, I'm going to talk about this course. So what is this course about? What are we going to learn in this class? So let me address that first. And in the second part of the video, I'm going to talk about programming languages in general. What are programming languages and how do we understand and comprehend programming languages? And finally, we will talk about how programming languages are implemented, which is going to be the subject of this entire semester. Okay, so let me start by talking about this course. Okay, so as I mentioned in some of the introductory posts I have already made, this course has two parts to it. And the two parts to it are really, we are going to learn a new programming language. And this language that we are going to learn is called Scala. Okay, and Scala stands for scalable, whatever it is, whatever that means, scalable language. It is an increasingly popular language. It works on top of what's called the Java virtual machine. Okay, so Scala works on top of the Java virtual machine, which is called the JVM. Okay, and it compiles to something called Java bytecode, which works on the Java virtual machine. So these are things that you can look up on the side. So Scala has, because of this link up with the Java virtual machine, Scala is highly interoperable with Java. So the programming language Java, which is a very popular programming language, interoperates very naturally with Scala. But more than that, Scala has some very big advantages. So it's going to be a functional programming language. In fact, I would say Scala is more of a general purpose programming language, but it implements this very interesting, it supports, let's say, this very interesting style of programming called functional programming. And in this course, one part of this course is going to just focus on learning about functional programming. So briefly, what is functional programming? Well, if you think about programming in a language like C, C++, you think about programs like this: int x equals 0, x equals x plus 1, if x greater than or equal to 1, then x equals x minus 1, don't forget the semicolon, else x equals x plus 2. So you can keep going. Now, the way you think of this program is as a sequence of commands or instructions. Okay, and this kind of a style of programming is called imperative programming. So you think of your program as a sequence of commands, and you focus more on how the control flows through the program. So you focus more on control flow, and you have mutable data. So you have variables called x, which is a cell in the memory in which new values are constantly stored and updated. This is one way of viewing programming. In the functional style, you view your program as functions. So you view your program as functions where smaller functions are used to write up bigger functions. So as an example, in this program, I could define a function, a composite function with two inputs, let's say x and y, and an output z. And the idea here is the composite function is built out of a simpler function f, another simpler function h, another simpler function g, where you want to say comp of xy is something like this. F of x is done, then h of y is done, and then the whole thing is applied to g. So if you want to think, I mean, this is not the essence. This is not the essence. Functional programming is a lot more than this. But if you want to think about some differences between an imperative style, a sequence of command style, whereas a functional style is more built on building up programs from little parts, and these little parts combine in some predetermined ways to build up big parts, as opposed to having programs be sequence of instructions. Okay. Now you might, some may immediately see the difference, and part of the difference here is there is no sequence of instructions that's explicit. What is explicit here is how functions are being composed and how values flow from inputs of one function to the output of another function. So there is more of an emphasis on building up the program from smaller parts, and there is more of an emphasis on how functions integrate into each other. Okay, and this is at a very high level, and I know this is going to be confusing to some of you, but at the end of this semester, I know that some of this will start to make sense. So in functional programming, we will be avoiding loops, while loops, control structures like while loops, for loops. Even though some for loops are allowed, we will be entirely avoiding loops. We will be entirely avoiding mutations. So we'll be entirely avoiding mutations or side effects. As much as possible, we are going to avoid having mutable states. And I'm going to show you how that's done. Okay, and it's going to be very surprising how that's done. Other things are, we are going to use things like functors, some things called map, reduce, filter, iterators. So there is this whole genre of concepts that are associated with functional programming, and one of the important parts of this course is we are going to learn that, and we are going to learn that using Scala as our target programming language. So that's goal number one for this class. Okay, so we are going to learn functional programming, and we are going to learn that with Scala. Okay, so the second part of this course is so we mentioned functional programming as the first part of this course. There is the more important business of this course, which is going to be understanding programming language internals. So understanding how can we define our own programming language. And in this class, we will be defining a very particular language we will call Lettuce. And Lettuce is going to be a toyed up version of a family of languages called ML, of which there are very popularly used languages like OCaml, F# from Microsoft, Reason from Facebook, Elm. So there is a bunch of these languages, SML-NJ, the New Jersey version of simple SML, standard machine language. So there is a lot of these, and these belong to a family called the ML family. So the language that we are going to be defining and learning from scratch is going to be this ML-like language, and this little language is going to be called Lettuce, and you will see why. And we are going to see, as we define various aspects of this language, we are going to see how we are implementing this language, okay? And this is going to be important. So we will see how we are going to implement these definitions. And of course, the implementation, remember, is going to be done inside Scala. So we are going to build an interpreter for Lettuce in Scala, okay? And we are going to, as we do this, we are going to learn some interesting choices that we can take when we are defining programming languages. And these choices are going to be very, very important, because we are going to use these choices to learn some very core programming language concepts. Like, for example, we are going to learn how programming languages like functional programming languages can treat functions as values. We are going to learn about higher order functions. The one very, very large and expansive topic is going to be type systems. So we are going to be learning about languages that are strongly typed and how do these languages do typing. Okay, and we are going to talk about how all of this works. Then we are going to learn about a little bit about languages with pointers and references and mutables, and these are called mutations or mutables. All right, different styles of mutables. We are going to, if time permits, we'll talk a little bit about garbage collection. We are going to learn about objects, even though I typically like to use Scala itself to learn about objects rather than implement objects in letters, though that can also be done. All right, so these are the core programming language concepts. Now, so part of the class is that we are going to build Lettuce from the scratch. So initially, Lettuce will have simple arithmetic is all it will have. And then we are going to introduce things like something called a let binding, and we are going to use that to study something called scoping. We are going to introduce something called, we are going to introduce functions. We are going to add recursion to this language. We are going to add types to this language. We are going to allow mutables to this language, various types of mutables. And eventually, we'll talk about, what does it take to add objects to this language. And along this way, the language starts to grow in complexity and start to become more of a full-fledged language. So this is going to be the main thread of this class. And in parallel, you're going to be learning a little bit about functional programming in Scala. And I'm going to keep the Scala part very stubbornly functional, which means that I'm going to thoroughly discourage you from doing any kind of imperative features in your Scala programming language. And you will see, the way I will do it is I won't even tell you about some of them, even though they exist in Scala. And in that sneaky way, unless you go in the internet and learn about them, you wouldn't know. But the better answer is we are actively going to show you some of these imperative features, but in this class, we are going to constrain you not to do that, so that you are going to appreciate the functional style if needed, with some force and with the force of grading, applied as pressure to do that. All right. So then comes the question, why? Why are we learning this? So there are many reasons we can learn this. A primary reason you might imagine, and you might imagine this to be the primary reason, that you can learn how to implement your own language. Not lean, but learn. Okay, so you can learn how to do your own language. And this is somewhat unlikely for most of us, right? 99.9999% of programmers don't create their own language, except that many people do create some what are called domain-specific languages, or DSLs. And these are very, very common inside large software systems. So yes, many people don't create their own big language. I mean, Java was created by a team of like 10 or 15 people. I mean, you don't have that many huge programming language teams that come up. But, there are lots of people who will work on creating their own DSLs for their very specific applications. So this is an important consideration, but not the primary consideration of this class. I would say the primary consideration of this class is to enable you to pick up a new language and run with it. And the way you need to understand that is by looking and studying one language and various implementation choices carefully. You know that there is nothing new under the sun. So there is very little that's going to be new under the sun. So everything you're going to try and learn in the future is going to be similar, at least in a passing way, to something you have learned in this class or something you will encounter as a result of what you've learned in this class. So it's going to be that principle that's going to make sure that you are going to have be able to pick up new languages as new languages become more and more popular. So that's number one, I would say, and that would be my number one reason. My number two reason is I would like to develop an appreciation for functional programming style. And, this appreciation that you can program functionally and there are lots of advantages to it, and some of it would be unlearn certain things, certain concepts that you take for granted when you are introduced into the C, C++, Python paradigm. Okay, and by the way, when I mentioned Python is a language that has very good support for functional programming style, even though you don't think of it naturally as a functional programming language. And the latest versions of C++, like C++ 17, has a lot of features like lambdas that will allow you to do functional programming. So lambdas, functors. There's a lot of features in the latest C++ that will allow you to do functional programming as well. So functional programming is not specific to a language. Those certain languages do support it better than certain other languages. So, and this would be my number two reason for this class. This would be my number two reason, which is important. You might end up in the industry doing JavaScript, and many of your colleagues will be doing functional programming or a reactive functional programming framework, and you would know then what they are doing, and how do you create anonymous functions, pass callbacks, how do you avoid using mutable states, what can you use instead of immutable states. Those are things you would have encountered in this class. Okay, and I would say learning how to implement your programming language to me comes in at number 3 because of the increasing popularity of domain-specific languages. All right, so I hope all of these reasons are reasons enough to appreciate the material in this class. Now, there is a fourth reason. And the fourth reason is that much of this material in this class is being presented as something that's pragmatic and important for computer science. But there is a very important connection that some of the ideas here and some of the mathematics behind PL, some of the mathematics that underlie PL are very old. They go back to the work of people like Alonzo Church in the 1920s, and back to the work of Bertrand Russell, a very famous philosopher, work that he did in the early 1900s, 1910s. Okay, so these are, way before computers were developed. Like these are at least half a century before modern computers started coming through. So the ideas here are PL deals with deeply mathematical ideas about the nature of computation, about what is computation, and what are the minimal things that you need to encode computation. So what kind of computations can you do? How do you express computation? And if you replace the word computation by simply the word functions, it turns out that you get back to a lot of this early work that inspired languages. So as an example, Alonzo Church worked on a framework called lambda calculus. Okay, and lambda calculus, we will cut our teeth a little bit with it. I'm going to show you how lambda calculus comes in this class. Okay, but lambda calculus directly inspired the development of the first AI programming language called Lisp by John McCarthy. Okay, and lambda calculus has inspired a lot of functional programming. Okay, so this is one very simple example of how a mathematical idea developed by Alonzo Church to understand what kinds of functions from natural numbers to natural numbers can be constructed, in a certain manner. You go from there to actual functional programming and languages like early languages like Lisp, which still exists. The latest, the greatest version is called Clojure, which is a Lisp that runs on JVM, just like Scala runs on JVM as well. Okay, so Lisp is a very active programming language. There are dialects of Lisp called Scheme and so on. Okay, so and these are directly inspired by lambda calculus. And in fact, our language Lettuce is just one step removed from lambda calculus. I will show this to you at some point. It is that anything you write in Lettuce has a direct translation to lambda calculus, very, very simple, direct. And anything you write in lambda calculus with a little bit of search and replace for some terms, you get a Lettuce program out of it. So we will see that these are actually so close that we call this a syntactic sugar. So our language Lettuce is just syntactic sugar for lambda calculus. Okay. And so we are going to study this idea. And what about Bertrand Russell? Well, Bertrand Russell dealt with some paradoxes in mathematics. Okay, and one of the paradoxes is called the Barber's paradox. What is the Barber paradox? So this is a little bit of a side note, not relevant to this class at all. So define a barber. So define a barber as a person, the set of all persons, a person who shaves all those who do not shave themselves. So define the set of all barbers as the set of all persons, the set of all people. The only thing is, a person is a barber if they shave all of those people who do not shave themselves. Then the question is, does a barber shave himself? What do you think? Well, here comes the paradox. You can think about it, and it turns out that a barber, if you think a barber shaves himself, then that person cannot be a barber. On the other hand, if a barber does not shave himself, then a barber must shave all those who do not shave themselves. So a barber must shave himself. So you get into trouble. So if a barber shaves himself, then cannot be a barber. So you get to a contradiction. On the other hand, if a barber does not shave himself, then you get to a contradiction too, because if a barber does not shave himself, who after all is a barber? By definition, it's a person who shaves all those who do not shave themselves. So a barber must shave himself. So barber must shave himself. Again, you get into a contradiction. So you cannot have this alternative or this alternative. Both of them are contradicted. So you get into absurdity. Now, Bertrand Russell, such paradoxes existed long before Bertrand Russell. But Bertrand Russell's main contribution was to recognize that this kind of contradiction poses serious issues in a key branch of mathematics which you have studied called set theory. So if you can define such nonsense sets, and by the way, you can turn this definition into a definition that involves more respectable things like numbers. The Barber's paradox is just like a language-based thing, but you can turn this into something that just involves numbers. Okay, I'm not going to do that. But the problem is you are able to define certain set whose existence contradicts itself, and that is bad. So to avoid this kind of a problem, what Bertrand Russell did was he tried to organize mathematical concepts into hierarchies called types. So you have types, and you have higher order types that are built on base types. Okay, and it turns out that after many about 100 years of research on this, this is a direct ancestor of types in programming languages. So one thing about this subject is PL tends to be a very pragmatic subject. After all, we are dealing with the very foundations, the fabric of computer science. PL also tends to be a very mathematical and highly philosophical subject because it intertwines itself deeply into mathematics. Okay, so and that's going to be the fun part of this class, and this is why I find working as in this area of research of programming language theory to be extremely fun, because one minute you're trying to implement a language and bring it to life, and another minute you're talking about its mathematical properties, and many programming language people these days love to delve in this abstract area of mathematics called category theory, and that's all the rage, and there is something called homotopy type theory, which is all the rage in mathematics these days, and it has its roots in PL as well. All right, so anyways, so PL is a very deep subject as well, something that you should encounter for its own sake if you are interested in further research, but there are numerous reasons to study this subject in this class. All right, so with this I will end this lecture here and see you in the next lecture. Thank you. Bye.